Hi, we're Vaughn and Claire from Timbu, and this is Deconstructing IoT. Today, we're bringing you along with us to meet John Gilbert, Executive VP and Chief Technology Officer of Rudin Management Company, one of New York City's largest privately owned real estate companies.
We'll speak with John about Dboss, or the Digital Building Operating System solution, which analyzes building occupancy, exterior weather conditions, and other data to forecast energy needs and to maximize energy efficiency. We're here with John Gilbert, Executive Vice President, COO, and Chief Technology Officer with Rudin Management Company. Today we're talking with John about Dboss, or the Digital Building Operating System solution, a fully implemented smart architecture application. Thank you so much for talking with us.
My pleasure.
For those of our audience who aren't familiar with Dboss, could you give us a brief introduction and how the project came about?
Sure. We were asked by Con Edison back in 2007 to be the commercial office petri dish for their smart grid demonstration project. And what that basically meant is that they wanted to study how bringing innate intelligence into the grid would be impacted in large office buildings. The first meeting we walked into, they showed us a chart that basically said there was a 45-second warning that they had prior to the lights going out in 2003. And the question they posed to us was, would that have been valuable to you as a building owner if we had given you an early warning? And we said, yes. Lights go out, elevators get stuck, people are stuck in the elevators. We ultimately then have to utilize all of our emergency generating capacity, or a lot of it, to lower those elevators one by one, get the fire department to open up those doors and let those people out. Our thought was, if we had that early warning, we could then program our elevators ultimately to take that signal, go to the closest floor while the electricity was still on, let people out. Worst case is a false positive. People were inconvenienced, but we thought that was well worth it in case of brownouts and blackouts. What we then realized was we didn't have a catcher's mitt. We didn't, even if they could send us that signal, we couldn't really catch it and then make that data actionable. So what we did was we looked at ourselves and said, first of all, let's file a patent and let's create an invention for this early warning device for our elevators. And then secondly, let's look at, we kept asking ourselves, your smartphone, your iPad has an OS. Why doesn't this 2 million square foot building have an operating system? Why is data that we collect every single day simply dumped? And we said, we've got to fix that. And not being the sharpest knives in the drawer, we figured that somebody else had already thought of it, created it, and we could go and implement it in our buildings. We went around the world and nobody had. So we said to ourselves, we have to create this. We have to create an operating system. We didn't do it for commercialization. We did it as a tool for our own buildings and our own philosophy of sustainability and resiliency within the Rudin portfolio. So we created a prototype. The people who we had met at Con Edison were actually from Columbia University, working with Con Edison. They were from the Center for Computational Learning, Roger Anderson and his team, and they were experts in machine learning algorithms. So what we saw was, and when we really started analyzing, and when Rudin's been at the smart building game since 1995, when we created 55 Broad Street, which many have said is the world's first smart building. So we had some innate intelligence, we had some background, but what we realized was the differential between of what makes a smart building smart is the ability to remember. Eric Kandel, who is a Columbia professor and Nobel Prize winner, and disproved Einstein in a way. Einstein said there's only one constant in the universe, and that's the speed of light. But Kandel proved that the chemistry of memory was also a constant. And we felt that was very, very interesting as we began to bring biology into our buildings. We've always had chemistry, we've always had physics, but now suddenly, the ability to remember and to learn from what we remember, what can be remembered, was really the key piece that differentiated one building from another, and that intelligence.
So in addition to partnering with Columbia University Engineering, I understand you also partnered with Celix ES to
Correct.
design the project. So with regard to those partnerships, could you speak a little bit about how those collaborations worked and what sort of technical challenges you faced designing and deploying a system with so few precedents?
Sure. I mean, what I always makes me laugh about the Internet of Things, and as people look at the Internet of Things, it's kind of this thought that the Internet of Things is, just kind of floats out there, right? Kind of like the cloud, right? People talk about the cloud. Well, cloud is really in our building at 32 Avenue Americas. It's a bunch of servers that you connect to that ultimately stores data. The Internet of Things doesn't float out in space. It exists within the built environment. And so as we created the prototype with Columbia University, we then looked at ourselves and said, do we build this ourselves or do we go look for an established partner? And we were introduced to Finmeccanica, which is a large Italian aerospace and defense contractor. They're the wholly owned, they own Celix ES. Their engineering subsidiary. And we entered into a contract for them to build this for us, take our invention and make it real, which they did. I think the biggest challenges were language. How do you get machines to talk to each other, that never had any ability to talk to itself in the first place? How do you solve that language barrier? How do you ultimately get your elevators to talk to your turnstiles, to talk to your chilled water, your chillers, to talk to your fans and your air distribution system? That, I think, was the biggest challenge. And I think the beauty of DBOSS is that it ultimately, now we take that data, when our engineers come in for the tomorrow morning or for this morning, they actually see a prescriptive and predictive pathway that all they need to do is follow for that day. And if they stay below that curve, the delta between the prescriptive and predictive path and the actual path is saved money. So for us at 345 Park Avenue, first year we saved almost $1 million, $980,000. At 560 Lexington, which is a smaller building, 300,000 square feet, we saved $1 a foot. So the ability ultimately not only to save money, but then from an operational standpoint, as you now suddenly have these disparate systems that never talk to each other, connected, you now are able to, our hot and cold calls declined by 45%. Because our engineers are seeing where there's a problem before the tenant even feels that problem and picks up the phone and says, I'm too hot, I'm too cold. So the ability to really take that data and to use it has been huge for us, and that truly is where the Internet of Things becomes relevant, right? How does it help us? How does it, if it's not a tool, we learned back in the 90s that if it's just cool, it's not going to last. It's got to be, as my wife would say, it has to have utility and beauty, or it's out. Well, this has to have, utility as well as money savings, and as well as the ability to create new relationships. For instance, in our buildings now, our normal load curve was a classic bell jar. Start up in the morning, peak midday, early afternoon, and drop off. Because we're now able to measure occupancy and create a relationship with our fan speed and our chilled water temperatures, we're able to do a little mini ramp down in the middle of the day. First thing we're able to do is to shrink our operational day. We now know we're able to measure the thermal inertia of our buildings so that we know exactly how much energy it takes to either heat up or cool down depending upon the day, so that we don't have to guess in the morning when we start up. And then we also know that the thermal inertia in reverse, in terms of how quickly a building cools off or heats up at the end of the day, we're able to measure that so we can shrink our operational day. And then you have the mini ramp down in the middle of the day, and it's a beautiful thing.
Can you tell us about some of the sensing systems you mentioned? You can detect occupancy and power outages. What other kinds of sensing systems?
We measure CO2, we measure water consumption, we measure all the different, and this gets a little bit nerdy, operational engineering nerdiness, but our return air temps, our outside air, it's really the physics, the thermodynamics of a building in terms of how much energy it takes to take either cold or hot air and then transform that into comfort air. I always, whenever I give a speech, I'm always reminded of my college physics professor who, drummed into us the first law of thermodynamics, that energy cannot be created or destroyed, it can only be transformed. So in a sense, we're off the hook. We don't have to create anything, we just have to transform what we already have. And as long as we look at that, and as long as we realize that that challenge is a far less steep mountain decline than actually having to create something, then I think we really have an opportunity and an advantage. And that's what DBOSS does. It creates that opportunity. What is our job? Our job really is to collect the data, which we always have. It's to remember that data now. It's to learn from that data. It's to express that data in a way that's intuitive, so that you look at a graph and immediately you get it. And then ultimately to share it with our customers as quickly as we can. So that intuitiveness, I can't stress that enough. It's so important that, and what DBOSS is, it's really a system that came from the heart of the building. Buildings have always had a heart, the engine room, the boiler room, right? It never had a brain. Buildings now have a brain. Now what we need to focus on, and I think this is where you're going with your question, is what does that central nervous system look like? What is that network of sensors that ultimately collects that data so that it can be expressed back in DBOSS? So DBOSS, our engineers, people always come in and we talk to them and they say, oh, it's so much training, and no training for our guys. They created it. They live this. It's like a video game to them. And they're constantly, and we meet every week, constantly tweaking it. Let's do this, let's try this, let's see what that relationship is. It sounds so basic for me to sit here and say that we changed our consumption curve with a little mini ramp down because we've ultimately put occupancy on top of chilled water temperature and air temperature. It sounds so obvious, and yet we never had a tool to be able to see it. Now we can see it, and now we can ultimately take that data and make it actionable.
And how important is granularity of data in a building-wide system? Is it important to look floor by floor, unit by unit at some of the data that's collected and the patterns there?
It's a great question. And as we really slice and dice the built environment, and as we build that central nervous system, we're learning, the big question was, how many points of data should we be monitoring? Is it 5 million? Is it 1 million? Is it 10 million? Is it 20,000? Don't know the answer yet. We know that more is not better. That we look at it, and again, it's all what your perspective is. Our job is to run real estate. So it's not to run a technology company, even though we're thinking now that where we used to be a real estate company that dabbled in technology, we now look at ourselves more as a technology company that dabbles in real estate. But we can't lose sight of what the goal is and what our job is, which is to run that real estate as efficiently and effectively as we possibly can.
So I've read about the cockpit-style control panels that operators can use to basically control the system based on all of the sensor information that's been gathered and processed. Is there any part of the system that is completely automated, such that if the system detects that there's a certain number of people on a floor and the weather is going to get cold, the heat would automatically turn on? Or is it all something that is viewed by the operator and then controlled?
Human in the loop is the key piece. Mm-hmm. So right now we're basically just making our operators more intelligent. Mm-hmm. But in the 2.0, which will be out later this year, we are introducing automation. What's important to note that not all buildings and not all systems can or should be automated. This belief that, in the Jetsons world of if you think about something, the toaster's going to turn on and your toaster's going to go in. Maybe that's okay in a residential home and an apartment, but for an office building that's got 2,000-3,000 ton chillers running, these are huge engines, and we want a human in the loop on those decisions. Now, in a building like this, where you have individual DX units on each floor, there's a real opportunity for automation because the machines are smaller, the systems are more decentralized, and you ultimately can automate that, and we are working towards that.
You mentioned learning algorithms, and I was wondering how the learning algorithms work. Are they more optimized for learning tenant preferences or energy efficiency, and can those two coincide? How do you balance the two?
The most fascinating thing about the algorithms that we use were that they were created to predict epileptic fits. So they are predictive and they are prescriptive. So and that's where, when I mentioned before that we're actually bringing biology into our buildings now to join the other sciences that we already utilize. So the algorithms themselves are really just, the first thing we do is we obviously have multiple data feeds coming in. So we've got weather, we've got time of the year, time of day, all Y and X axis are based upon time, obviously, because that's the X axis is time, Y axis is the variable of what we're measuring, whether it's CO2 or water or air temperature or outside air temperature. So the algorithms themselves, to me it's fascinating because they learn very quickly. We had a situation 2 summers ago, I don't know if you remember, where we had 5 straight days of the independent systems operator telling us we should be shedding load because it was going to be so hot. We'd never had that 5 days before. So Dboss, when we look at the graph that Dboss charted for those days, we literally, where it's a normal day, it's a double humped camel. It was a single hump camel because we were shedding load at 1 o'clock, 2 o'clock in the afternoon. So we went through 5 days of that. Monday we come back, the weather broke. Dboss is like, hey, that was pretty cool. We did last week with shedding load, let's do it again. We're like, no. That was something that we got to get back to the old game here, Dboss. And within the next week, Dboss saw the patterns reappear and then redrew those curves. So it's fascinating to me that, I use the analogy that from a blackjack standpoint, it's almost like we're counting cards because you're literally able to see what's coming next. I know tomorrow, based upon weather predictions and occupancy predictions and time of year predictions, pretty much what the load of all of our buildings, 8 million square feet that we've got currently operating, what those load curves are going to look like. Now, why does that matter? It matters from an energy procurement standpoint. We're really excited about that. We think that's the killer app for our commercial office buildings. We think on the residential side, it's water consumption patterns, ultimately preventing and predicting or monitoring leaks within the building is hugely important. So each vertical that we go into will have its own killer app that will be most significant and most important to that particular real estate vertical. I think procurement across the board, but then as we look at whether a human is living there or working there or being fed there or buying stuff in a retail situation or being treated for health issues in a hospital or learning in a university, each of those verticals has unique characteristics that we're going to go after.
So how many buildings are currently running the DBOSS system and how many occupants?
Roughly, well, just in 345 Park alone, which is 2 million feet, we've got 5,500 people daily come into that building. So extrapolate that over, you're probably in the 20,000 or more people range in our office buildings. We're just starting to do 2 residential buildings. Those are roughly close to 800 units in those 2 buildings. So we're beginning to learn. I mean, the beauty of this is that no one's ever gone here before, so we learn every day. You know, when you look at the Internet of Things, it's not easy to find true practical applications. A lot of it's still theory, and a lot of it's still, you know, in the test tube, and it wasn't because we had a brilliant plan to do this, it's just because we got there and we saw the utility of this system and we wanted this system that we got there first. So we're excited about that, and we're excited about our opportunity to learn something new every day. And DBOSS, I think, if a machine can be excited or an algorithm can be excited, I think it's excited about what it learns every day too.